Summer 1940. Royal Air Force Hornchurch Airfield, Essex. Two identical Supermarine Spitfires sit on the concrete apron. Same Merlin engine, same 8-gun armament, same pilot strapped into the cockpit. Squadron leader Desmond Cook throttles up the first aircraft. Takeoff run, 320 yards. Climb to 20,000 feet, 11 minutes, 8 seconds. Service ceiling where the air grows thin and engines gasp, 32,000 feet. 20 minutes later, Cook climbs into the second Spitfire. Identical airframe, identical engine, different propeller. Takeoff run, 225 yards. Climb to 20,000 feet, 7 minutes, 42 seconds. Service ceiling, 39,000 feet. Same plane, same engine, same war hanging in the balance. The difference between victory and defeat in the Battle of Britain came down to 3 spinning aluminum blades that aviation experts across America had dismissed as impossibly complex. Frank Caldwell's impossible propeller design, the one that would make U.S. bombers fly 100 miles per hour faster, had just revealed itself over the English countryside. But the story of how one stubborn engineer's numbers defeated an entire industry's assumptions begins 8 years earlier, in a factory where everyone said his idea would never work. Frank Walker Caldwell stood in the oil-stained test facility of Hamilton Standard Propeller Corporation, East Hartford, Connecticut, on a gray February morning in 1932. At 43, the MIT-trained mechanical engineer had the methodical bearing of a man who trusted numbers over opinions. Wire-rimmed glasses perched precisely on his nose, clipboard never far from his calloused hands. Behind him, mounted on a test stand that vibrated with mechanical fury, spun a gleaming metal propeller unlike anything in aviation. 3 aluminum blades that could change their angle while rotating at 2,400 revolutions per minute. The telephone call that would change everything had come 3 days earlier from Boeing Field in Seattle. The Boeing Model 247, America's revolutionary new airliner, sat stranded at Denver Municipal Airport like a thoroughbred limping on broken legs. At an altitude of 5,280 feet, the twin-engine marvel that was supposed to fly passengers coast to coast in record time struggled to climb over the Rocky Mountains. 2 wooden propeller blades fixed at a single pitch angle optimized for one flight condition rendered the aircraft nearly useless everywhere else. Pan American Airways. President Juan Trippe had delivered an ultimatum to Boeing that morning. Fix it or we're buying Douglas. The stakes couldn't be higher. United Airlines had 25 Model 247s on order. TWA wanted 30. But none of that mattered if the most advanced airliner in the world couldn't clear a mountain range. Caldwell had heard this song before. Across America's aviation community, the conventional wisdom flowed like gospel from hangar to boardroom. Variable pitch propellers were a solution looking for a problem. Too heavy for the performance gain, too complex for reliable operation, too many precision machined moving parts operating in a hostile environment where oil froze at altitude and vibration destroyed delicate mechanisms. The Army Air Corps Engineering Division had officially classified Caldwell's hydraulic design as mechanically unsound. Even Charles Lindbergh, aviation's most celebrated voice, had questioned the concept during a private meeting at Wright Field the previous autumn. But Caldwell possessed the quiet confidence of an engineer who had been proven right before. As the government's chief propeller engineer from 1917 to 1928, he had watched aviation experts resist metal propellers because wood was lighter, then oppose ground-adjustable props because of unnecessary complexity. Each time, his data had demolished their assumptions. Each time, the industry had eventually followed where his numbers led. This time felt different. This time, careers and companies hung in the balance. Hamilton Standard had invested everything in Caldwell's revolutionary design. 800 jobs in East Hartford, plus manufacturing contracts that stretched from Connecticut to California. The company that had built propellers for Lindbergh's Spirit of St. Louis might not survive if Caldwell's calculations proved wrong. His own reputation, built over 25 years of propeller development, rested on 3 spinning blades and a hydraulic governor system that used engine oil pressure to automatically adjust blade angle based on flight conditions. The engineering was elegant in its simplicity. During takeoff and climb, when maximum power was essential, the propeller automatically shifted to fine pitch, like a car's low gear, allowing the engine to spin faster and generate more thrust. At cruising altitude, the system shifted to coarse pitch for maximum speed and fuel efficiency. If an engine failed, the propeller could feather its blades parallel to the airflow, eliminating drag that would otherwise pull the aircraft into a fatal spiral. The numbers spoke with mathematical certainty. Caldwell's wind tunnel tests at MIT had proven that constant speed propellers could increase climb rate by 40%, extend service ceiling by 7,000 feet, and improve fuel efficiency by 15% across all flight regimes. But numbers meant nothing if the aviation industry refused to believe them. The breakthrough came on February 15, 1933, when United Airlines President Pat Patterson gave Hamilton Standard one final chance, one test flight with their impossible propeller installed on a Boeing 247. Test pilot Eddie Allen, a former Navy aviator with ice water in his veins, would put Caldwell's theory to the ultimate test over the same Rocky Mountain terrain that had grounded identical aircraft 2 weeks earlier. Allen climbed steadily past 6,000 feet, the altitude that had defeated the fixed-pitch 247, then 8,000, then 10,000 feet, crossing the Continental Divide like it was a speed bump on a country road. The constant speed propeller adjusted automatically to each altitude change, maintaining optimal engine RPM while maximizing thrust. Where the fixed-pitch aircraft had struggled to reach 6,000 feet over Denver, the modified 247 achieved a service ceiling of 20,700 feet. The cruise speed improvement was equally dramatic, 15 miles per hour faster across all altitudes with 12% better fuel efficiency at normal cruise power settings. Patterson received the test results by telegram that evening. Constant speed propeller exceeds all performance claims. Recommend immediate adoption for entire United fleet. But as orders poured into Hamilton Standard's East Hartford facility, a darker reality was emerging on the global stage. In Germany, the Nazi Party had seized power. In Japan, military leaders spoke openly of Pacific expansion. War clouds were gathering over Europe and Asia, and the propeller technology initially designed for airline passenger comfort was about to become America's secret weapon. The telephone rang in Caldwell's office on a humid May afternoon in 1933. The caller identified himself as Commander John Towers from the Navy Department's Bureau of Aeronautics. They wanted to discuss fighters, fast fighters that could outclimb and outrun anything the Germans or Japanese were building, and bombers that could fly higher and faster than enemy interceptors could reach. The age of aerial warfare was dawning, and Frank Caldwell held the key that would unlock American air superiority. The telegram arrived at Hamilton Standard on November 13, 1933, bearing news that would validate everything Frank Caldwell had fought to prove. The National Aeronautic Association announced that Hamilton Standard Propeller Corporation had won the Collier Trophy, aviation's highest honor, for development of a controllable pitch propeller, with particular credit to Frank W. Caldwell. President Franklin Roosevelt would personally congratulate him at a White House ceremony in December. But even as photographers captured Caldwell shaking hands with the president, the aviation establishment remained stubbornly skeptical. At Wright Field in Dayton, Ohio, Army test pilots complained bitterly about the extra complexity that constant speed propellers introduced into combat aircraft. Major Benjamin Kelsey, chief of the Army Air Corps Fighter Projects Office, voiced the concerns that echoed through military hangars across the country. What happens when that hydraulic system fails over Germany? When oil pressure drops and the propeller locks up? Fixed pitch, props don't break down because there's nothing to break. Caldwell's response was characteristically methodical. If military aviators demanded proof of reliability under combat conditions, he would give them data that left no room for doubt. Working 18-hour days in Hamilton Standard's expanded test facility, he invented what became known as the whirl test, mounting propellers on fixed stands to measure thrust, endurance, speed, and structural strength under extreme conditions that exceeded anything aircraft would encounter in actual combat. The technical breakthrough that made everything possible was elegant in its mechanical simplicity. Caldwell's hydromatic propeller used engine oil pressure to drive a piston that changed blade angle through a system of gears and counterweights. A centrifugal governor, no larger than a coffee can, maintained constant RPM regardless of flight conditions by automatically adjusting blade pitch. When the aircraft climbed and air density decreased, the propeller automatically shifted to fine pitch, aviation's equivalent of low gear, to maintain engine RPM and maximize power. During cruise flight, the system shifted to coarse pitch for maximum speed and fuel efficiency. If engine RPM climbed too high during a dive, the propeller automatically coarsened pitch to prevent overspeed damage. Most revolutionary was the feathering capability. If an engine failed completely, oil pressure from the remaining engines could rotate the dead propeller's blades parallel to the airflow, eliminating the massive drag that would otherwise pull a multi-engine aircraft into an uncontrollable spiral. For bomber crews flying deep into enemy territory, this single feature could mean the difference between limping home on remaining engines or becoming another lost statistic. The performance improvements were undeniable when translated into combat capability. A P-51 Mustang equipped with Caldwell's constant-speed propeller versus the same aircraft with fixed-pitch blades showed dramatic differences across every flight regime. Takeoff distance was reduced by 30%, allowing fighters to scramble from shorter airfields closer to the front lines. Rate of climb increased by 40%, cutting precious minutes from the time required to reach intercept altitude. Service ceiling jumped by 7,000 feet, giving American fighters altitude superiority over enemy aircraft. Combat range extended by 200 miles, and fuel efficiency improved by 15% across all power settings. But numbers on test reports meant nothing if the propellers failed when pilots needed them most. Caldwell's obsession with reliability drove him to test every component beyond its design limits. Propeller blades were subjected to loads 50% higher than maximum combat stress. Hydraulic governors operated continuously for 500 hours at temperature extremes from 40 degrees below zero to 160 degrees Fahrenheit. Oil seals were tested with contaminants that simulated combat damage and maintenance neglect. The resistance from established aviation manufacturers grew more vocal as Hamilton Standard's order books filled with military contracts. Curtiss-Wright, manufacturer of fixed-pitch propellers for most Army Air Corps fighters, launched a lobbying campaign arguing that constant-speed propellers were an unnecessary complication that will cost American pilots their lives. Their chief engineer, Dr. George Meade, published technical papers questioning whether hydraulic systems could operate reliably at combat altitudes where temperatures dropped to 60 degrees below zero and oil viscosity increased dramatically. Caldwell answered with more data. His cold weather tests at 35,000 feet proved that the hydromatic system actually performed better at high altitude because thicker oil provided more positive pressure control. Vibration tests showed that constant-speed propellers suffered fewer mechanical failures than fixed-pitch designs because automatic pitch adjustment eliminated the resonance frequencies that cracked propeller hubs and loosened mounting bolts. The breakthrough moment came during a demonstration at Selfridge Field in Michigan on March 21, 1934. Two identical P-26 fighters took off simultaneously, one equipped with the standard fixed-pitch propeller, the other with Caldwell's constant speed system. The performance difference was so dramatic that observing pilots initially suspected the constant speed aircraft carried a more powerful engine, timed to 10,000 feet. 8 minutes 30 seconds for the fixed-pitch fighter, 5 minutes 40 seconds for the constant-speed version. Maximum speed at 15,000 feet, 187 miles per hour versus 203 miles per hour. Service ceiling, 28,000 feet versus 34,500 feet. Lieutenant Colonel Carl Spaatz, who would later command all American strategic air forces in Europe, filed a report that evening recommending immediate adoption of constant-speed propellers for all Army Air Corps fighters and bombers. The performance advantage, he wrote, is so significant that it represents a fundamental shift in combat capability. Any Air Force equipped with constant-speed propellers will possess decisive superiority over opponents using fixed-pitch systems. As 1934 ended, Hamilton Standard's production lines operated around the clock to meet orders from the Army, Navy, and civilian airlines. But across the Atlantic, darker events were unfolding that would test Caldwell's innovation under conditions no peacetime engineer could imagine. While Frank Caldwell refined his propeller designs in Connecticut, European aircraft manufacturers lagged dangerously behind American innovation. In the sprawling Messerschmitt factories outside Augsburg, Germany's most advanced fighter, the Bf-109, still relied on manually adjustable propellers that required pilots to constantly manipulate pitch levers during combat. British Supermarine Spitfires and Hawker Hurricanes used primitive two-position propellers that offered only coarse pitch for high-speed flight or fine pitch for climbing, with no intermediate settings and no automatic adjustment capability. The deadly consequences of this technological gap became apparent during the first months of war. RAF combat reports from September 1939 painted a grim picture that kept Air Ministry officials awake at night. German Bf-109s consistently outclimbed British fighters above 15,000 feet, where manually adjusted propellers gave Luftwaffe pilots a crucial advantage. RAF bomber crews reported aborting missions when their aircraft couldn't reach sufficient altitude to clear the Alps or avoid German interceptors. Fighter command pilots lost precious seconds during climbs to intercept altitude, seconds that often meant the difference between engaging enemy bombers before they reached their targets or watching helplessly as German formations disappeared into cloud cover. Air Marshal Hugh Dowding, the methodical Scotsman who commanded Fighter Command, privately worried that Britain's fighters were technologically outmatched in the coming battle for air superiority. Intelligence reports from France described German pilots who could optimize their aircraft performance throughout an engagement, while RAF pilots struggled with manual pitch controls that demanded constant attention during the precise moments when focus should remain on enemy aircraft. At the 1938 Society of Automotive Engineers conference in Detroit, Caldwell presented data that should have alarmed every military aviation expert in attendance. His comparison of constant speed versus fixed pitch performance using identical engines revealed numbers that bordered on revolutionary. Static thrust, the power available for takeoff and initial climb, was 40% higher with automatic pitch control. Climb rate below 10,000 feet increased by 35%. Fuel consumption at cruise altitude dropped by 15%. Most significantly, combat ceiling increased by more than 6,000 feet, giving properly equipped fighters a decisive altitude advantage. Yet European aviation engineers dismiss these figures as theoretical advantages with practical disadvantages that will prove fatal in combat conditions. Dr. Ernst Heinkel, designer of Germany's fastest fighters and bombers, publicly argued that hydraulic propeller systems represented American over-engineering that sacrifices reliability for marginal performance gains. British propeller manufacturers echoed these sentiments, insisting that manually controlled pitch provided pilots with more precise control during combat maneuvering. The production challenge facing Hamilton Standard grew more daunting with each passing month as military orders multiplied. Each constant speed propeller required 47 precision machine components, with tolerances measured in thousandths of an inch and assembly procedures that demanded skilled craftsmen working with specialized tools. The company's East Hartford factory expanded to operate 3 shifts, 7 days a week, but demand consistently exceeded capacity as the Army Air Corps, Navy, and Allied purchasing commissions competed for limited production. Quality control became Caldwell's obsession and his nightmare. A single batch of faulty governors, the critical components that regulated oil pressure and controlled blade pitch, caused 3 propellers to lose hydraulic pressure during test flights at Wright Field. The failures occurred during simulated combat maneuvers, exactly the conditions where reliability was most crucial. Army Air Corps procurement officers threatened to cancel pending orders worth $12 million. Critics throughout the aviation industry seized on the incidents as proof that constant speed propellers were too complex for combat conditions where simplicity equals survival. Caldwell's response demonstrated the methodical determination that had driven his career. Working with a team of Hamilton Standard's best engineers, he redesigned the governor system in 6 weeks, implementing redundant pressure circuits and backup mechanical controls that would maintain basic propeller function even if the primary hydraulic system failed completely. New testing protocols subjected every propeller to stress levels that exceeded combat conditions by 50%. Most significantly, Caldwell instituted a policy of personally inspecting and signing off on every propeller shipped to military customers. The reliability improvements came at a critical moment. By early 1939, Luftwaffe strength had grown to over 4,000 aircraft, while RAF Fighter Command possessed fewer than 700 operational fighters. German aircraft production was accelerating rapidly, with new factories producing advanced designs like the Bf-109E model and the twin-engine Bf-110 destroyer. Intelligence reports indicated that German bombers possessed the range and ceiling to reach any target in Britain, while RAF fighters struggled to intercept high-altitude formations. The technological disparity became tragically apparent during the Battle of France. RAF Hurricane and Spitfire squadrons, equipped with two-position propellers, found themselves consistently outperformed by German fighters above 20,000 feet. Flight Lieutenant Douglas Bader, commanding 242 Squadron, reported that German aircraft climb away from us at will above 15,000 feet. Our propellers simply cannot provide the power needed for sustained high-altitude combat. Squadron losses mounted steadily as RAF pilots discovered that their aircraft's performance envelope was fatally inadequate against opposition that could choose when and where to engage. By June 1940, with German armies advancing toward the Channel coast and the Luftwaffe preparing for the assault on Britain, Fighter Command faced a technological crisis that threatened the outcome of the entire war. The same constant-speed propellers that American test pilots praised as revolutionary remained largely absent from RAF squadrons, victims of bureaucratic inertia and industrial resistance to change. Squadron Leader Desmond Cook, of 6'5". Squadron at Hornchurch understood better than most what his pilots faced in the coming battle. Having flown Spitfires against German fighters over France, he knew that RAF performance deficits weren't matters of pilot skill or aircraft design. They were engineering problems with engineering solutions. As Luftwaffe formations massed across the Channel for Operation Eagle attack, Cook prepared to make an urgent request that would test whether British bureaucracy could adapt fast enough to save Fighter Command from technological obsolescence. Squadron Leader Desmond Cook stood in the operations room at RAF Hornchurch on June 10, 1940, studying intelligence photographs that confirmed his worst fears. Luftwaffe formations were massing at airfields across northern France, Stukas, Heinkels, Dorniers, and the dreaded Messerschmitt escorts that had dominated the skies over France. Within weeks, perhaps days, they would come for Britain, and Fighter Command would meet them with aircraft that climbed too slowly and couldn't reach the altitudes where battles would be won or lost. Cook had flown Spitfires over Dunkirk, watching helplessly as German fighters climbed away from his squadron at will above 20,000 feet. The mathematics were brutally simple. His aircraft took 11 minutes and 8 seconds to reach 20,000 feet, while Messerschmitt Bf-109s could achieve the same altitude in under 9 minutes. In aerial combat, those extra 2.5 minutes represented the difference between intercepting enemy bombers before they reached their targets and arriving too late to prevent devastation. The solution existed in American factories, but British bureaucracy moved with glacial slowness, while German invasion preparations accelerated daily. Cook bypassed normal channels and placed a direct call to de Havilland Propellers, the British licensee for Hamilton Standard's constant-speed designs. His request was urgent and specific. Retrofit his squadron's Spitfires with American-designed propellers immediately, regardless of official approval or procedural requirements. The conversion program began within 48 hours, operating under emergency authorization from Air Marshal Dowding himself. De Havilland engineers worked around the clock in requisitioned hangars at Hatfield, modifying Spitfire MQ-1s from obsolete two-position propellers to fully automatic constant-speed systems. Each conversion required 8 hours of precision work, removing the old propeller hub, installing hydraulic lines, calibrating the governor system, and conducting ground tests to ensure proper operation. Fighter Command could spare aircraft for only 24-hour periods, creating a logistical nightmare where squadrons operated with reduced strength while their aircraft underwent emergency modifications. The first converted Spitfire rolled out of the Hatfield hangar on June 15, 1940. Cook personally conducted the initial test flight, taking off from the grass airfield in aircraft serial number K9847. The improvement was immediately apparent during the takeoff roll. The propeller automatically adjusted to fine pitch, allowing the Merlin engine to develop maximum power while maintaining optimal RPM. Where his previous aircraft had required 320 yards to become airborne, the modified Spitfire lifted off in 225 yards. But the real revelation came during the climb test. Cook throttled to maximum continuous power and began his ascent toward 20,000 feet, the altitude where Fighter Command expected to engage German bomber formations. The constant speed propeller adjusted continuously as air density decreased, maintaining engine RPM while automatically optimizing blade angle for maximum thrust. At 5,000 feet, 10,000, 15,000, the Spitfire climbed with authority that Cook had never experienced in 3 years of flying the type. 20,000 feet, 7 minutes, 42 seconds, nearly 4 minutes faster than his previous best time in an identical aircraft. Cook continued climbing, watching his altimeter register heights that would have been impossible with the old propeller. 35,000 feet, 37,000. At 39,000 feet, where the air was so thin that his breath frosted inside the cockpit, despite summer temperatures at ground level, the Spitfire finally reached its performance ceiling. The tactical implications were staggering. Fighter Command had been planning defensive tactics based on aircraft that struggled to reach 32,000 feet and required over 11 minutes to climb to intercept altitude. Suddenly, RAF fighters could operate 7,000 feet higher and reach fighting altitude in 2/3 the time. German bomber formations flying at 25,000 feet, previously safe from effective interception, now faced Spitfires attacking from above with energy advantage. Cook landed at Hornchurch and immediately telephoned Fighter Command headquarters. His report was terse and urgent. "The Spitfire is now an airplane. Request immediate conversion of entire squadron." Within 72 hours, all 12 operational Spitfires of 6.5 Squadron had been retrofitted with constant speed propellers. The pilots' reactions ranged from amazement to disbelief as they discovered aircraft performance they had never imagined possible. Flight Lieutenant Brian Lane, a veteran of the French campaign, described the transformation in his combat diary. "It's as if someone replaced our engines with twice the power. We can climb with the 109s now, match them altitude for altitude. For the first time since this war began, we're not fighting at a disadvantage." Similar conversions began immediately across Fighter Command, with de Havilland engineers working 18-hour shifts to retrofit Spitfires and Hurricanes before the German assault began. The numbers that would save Britain were becoming reality across Fighter Command airfields. By September 1940, 90% of RAF fighters carried constant speed propellers. Combat reports from the early phases of the Battle of Britain documented the dramatic change in tactical capability. RAF climb rate advantage allowed Fighter Command to reach intercept altitude 2 to 3 minutes faster than German estimates. Service ceiling superiority of 4,000 feet above German fighters meant that Spitfires could attack from positions where Messerschmitt pilots couldn't effectively respond. Most significantly, improved fuel efficiency extended patrol time by 45 minutes, allowing RAF squadrons to maintain standing patrols over German approach routes. The strategic impact extended beyond individual aircraft performance. Air Chief Marshal Dowding's defensive system depended on radar early warning and rapid scramble response to meet German formations before they reached their targets. Every minute saved in climb to altitude multiplied the effectiveness of Fighter Command's limited resources. Pilots who had spent the summer of 1939 watching German aircraft escape to higher altitudes now found themselves able to choose when and where to engage. The transformation was perhaps most evident in pilot workload reduction. Constant speed propellers eliminated the need for manual pitch adjustment during combat, freeing pilots to focus entirely on tactics and gunnery rather than engine management. German pilots, still struggling with manually controlled propellers, found themselves at a severe disadvantage when RAF fighters appeared above them with altitude and energy superiority that British aircraft had never possessed before. As Luftwaffe formations massed across the Channel for the final assault on Britain, Fighter Command waited with aircraft that bore little resemblance to the fighters that had struggled over France just months earlier. Frank Caldwell's impossible Propeller had given the RAF the performance margin that would determine whether Britain survived or fell to German invasion. America's entry into the war following Pearl Harbor transformed Hamilton Standard from a specialized manufacturer into the linchpin of Allied air supremacy. Every B-17 Flying Fortress, B-24 Liberator, P-51 Mustang, P-47 Thunderbolt, and P-38. Lightning required Caldwell's propellers to achieve their combat potential. The production demands were staggering beyond anything peacetime industry had imagined. By 1942, Hamilton Standard's order books showed contracts for 530,135 propeller assemblies, enough to equip every combat aircraft in the American arsenal and provide spares for continuous operations across multiple theaters of war. The East Hartford factory that had employed 800 workers in 1932 now sprawled across multiple sites with 22,000 employees working 3 shifts around the clock. Manufacturing partnerships extended to Frigidaire, Nash Kelvinator, and Remington Rand as automobile and appliance companies retooled their assembly lines for aircraft propeller production. Peak monthly output reached 12,000 complete propeller assemblies, each requiring precision machining that demanded tolerances measured in thousandths of an inch. But mass production created unprecedented quality control challenges that haunted Caldwell's nights and dominated his days. Failure rates increased as inexperienced workers struggled with complex assembly procedures. Statistical analysis revealed a disturbing pattern. Propellers manufactured during peak production periods showed higher malfunction rates than units built during the careful pre-war era when skilled craftsmen personally inspected every component. The crisis reached its peak over the industrial city of Schweinfurt on October 14, 1943. B-17 serial number 4, 2310. 4-1, nicknamed Hell's Angels by its crew, was fighting for altitude after flak bursts damaged its number 3 engine over the target area. The feathering mechanism, designed to eliminate drag by rotating failed engine propellers parallel to the airstream, engaged normally, allowing the bomber to maintain formation during the bomb run. But during the climb to escape altitude, a manufacturing defect in the hydraulic governor caused the feathered propeller to slowly rotate back into the airstream, creating massive drag that pulled the B-17 into an uncontrollable dive. 9 airmen died when Hell's Angels crashed in a Bavarian forest. The subsequent investigation traced the failure to contaminated hydraulic fluid that had frozen solid at 30,000 feet, preventing the governor system from maintaining blade position. Quality control inspectors found similar contamination in 47 propellers from the same production batch, all shipped to 8th Air Force squadrons operating from English bases. Frank Caldwell, now 54, and bearing the weight of industrial responsibility that no peacetime engineer could have imagined, took personal accountability for the failure. He flew to England on a War Department transport, meeting with bomber crews at bases across East Anglia to understand exactly how his propellers performed under combat conditions. The conversations were brutally honest. Technical Sergeant Michael Romano, flight engineer on a B-24 crew, described propeller failures that had cost his squadron 3 aircraft in 2 weeks. "The feathering system works fine in training flights over Kansas," Romano said. "But over Germany, with flak fragments and battle damage, these complex systems fail when we need them most." Caldwell returned to Connecticut and immediately redesigned the feathering mechanism, implementing redundant hydraulic circuits and backup mechanical systems that could maintain blade position even if primary controls failed completely. New quality control protocols subjected every propeller to environmental tests that simulated combat conditions, temperature cycling from 60 degrees below zero to 140 degrees above, vibration testing that exceeded combat stress by 75%, and contamination trials using hydraulic fluid deliberately polluted with metal particles, ice crystals, and chemical residues that might accumulate during extended combat operations. By 1943, the reliability improvements had created the most dependable propeller system in aviation history. Combat loss statistics from the European theater showed that propeller-related failures had dropped to less than 1% of total mechanical problems, lower than engine failures, landing gear malfunctions, or electrical system breakdowns. The feathering system that had initially caused problems now routinely saved aircraft and crews. 8th Air Force operational records documented hundreds of bombers that returned safely to England after losing one or more engines over German territory, their constant speed propellers automatically feathering to eliminate drag and allow continued flight on remaining engines. The strategic impact became evident when American aircraft began encountering German and Japanese fighters in large-scale combat. P-51 Mustangs equipped with Caldwell's propellers demonstrated decisive performance advantages over Messerschmitt Bf-109. K models, 30 miles per hour speed advantage and 5,000 feet of ceiling superiority that allowed American pilots to choose when and where to engage. B-17. Flying Fortresses could cruise 50 miles per hour faster than comparable German bombers while operating 8,000 feet higher, placing them beyond the effective ceiling of most Luftwaffe interceptors. The Pacific Theater revealed even more dramatic advantages. P-47. Thunderbolts, initially dismissed as too heavy for fighter combat, achieved 40% better climb rates than Japanese Zero fighters when equipped with constant speed propellers. The automatic pitch control allowed American pilots to maintain optimal engine performance during the rapid altitude changes that characterized Pacific air combat, while Japanese pilots struggled with manual propeller controls that demanded constant attention during precisely the moments when focus should remain on enemy aircraft. General Carl Toohey Spotts, commanding U.S. strategic air forces in Europe, summarized the transformation in a confidential report to the Pentagon. The constant speed propeller has given American aircraft decisive performance advantages in every theater where we operate. It is as strategically important as radar, long-range navigation, or any other single technology we possess. Statistical analysis conducted by the Army Air Forces in 1945 revealed that constant speed propellers had directly prevented an estimated 15,000 Allied aircraft losses through improved climb performance that enabled escape from enemy fighters, higher service ceilings that allowed operations above interceptor altitudes, feathering capability that permitted safe return after engine failures, and better fuel efficiency that reduced forced landings due to fuel exhaustion. Frank Caldwell's impossible propeller, dismissed by experts as too complex for combat operations, had proven more reliable under battle conditions than the fixed-pitch designs it replaced. The technology that skeptics claimed would cost American lives had instead saved thousands of airmen while providing the performance margins that made Allied victory possible.